the most important thing that you need to improve is the speed, the fault isolation speed. And there we do need a substantial improvements by almost a factor of 10 to the power of 3. So it's 1,000 times faster fault isolation. And that can no more be achieved with electromechanical components. You need to introduce semiconductor solutions. These are then called the solid-state breakers.
Welcome to this episode of Podcast for Engineers. It's the podcast you just have to listen to if you're interested in what's going on in the semiconductor marketplace. I'm your host, Peter Balint, and today we are joined by Leo Aichriedler, who is a distinguished engineer here at Infineon, mainly working in high-voltage solid-state power distribution, and specifically the solid-state circuit breaker, which is what we're here to talk about today. And in our series of We Power AI podcast, we've been looking at different systems which deliver clean and reliable energy because we have this situation where AI is using so much of it. But today we look at the circuit breaker. And of course, something is changing here too. That's why we're here to talk today. So
Absolutely.
What's pushing this change with the circuit breakers in the modern AI data centers?
Well, if you look at the past, in the past, all data centers were basically using as the traditional distribution scheme, mainly based on AC systems, and for sure having a critical infrastructure distribution system. So it's basically power coming in from the grid and then getting distributed to the loads. And for sure there was like a uninterruptible power supply as a backup system, but and some local gen sets or whatever, but it was all AC. Now, obviously, with AI coming into the game, the power demand is increasing dramatically. So now we need multiple sources to supply the data centers, and they have a different nature. So there might be for sure the grid, but there might be like PV infits, there might be large-scale battery storages to overcome the peaks. There are backup units and the like. And this means we have to support multiple sources and connect them to these loads. And the sources can be of dual nature. They can be like AC loads, AC supplies from the grid, but they can also be of DC nature, like the PV infit or the batteries. And we need to blend them and supply the loads. And the next thing that is also interesting is the servers, they are for sure a DC nature. They need DC. And since some of the sources are also of DC nature, it makes sense to distribute DC to avoid multiple conversions, DC to AC, AC to DC. It's just more efficient if you distribute DC in one domain. And another factor is for sure the distribution voltage. So far, typical voltages were like 230 volts or 400 volts AC. Now, if we go so high with the power levels, it makes sense to also increase the voltage because the current is just going insane with this relatively low voltages. So you want to increase the voltage level as well. And there it makes sense. We do see that like voltages in the regime of 400 volts DC are introduced, but some are already going into 800 volt DC. In some other segments, in some other parts of the industry, we already see like 1500 volts to max out the low voltage regime. And some are even exceeding that low voltage barrier, I would call it, going beyond the 1500 volt into the medium voltage range. So now with this change we make sure we can distribute a lot of power. And by reducing the currents, we have to use less copper. Copper is a very precious material. And you want to get the best out of the copper that you need to employ. But on the other side, you want to reduce the effort you have in routing the power to your load. And there's one connecting element. If you have these multiple sources, you have your loads. For sure, there's the copper in between, but the connecting element, the smart element, is then the circuit breaker, because you need to connect, you need to isolate, in case of a fault, you want to isolate the individual sources, they can also fail. And you want to have a means to protect the downstream loads and or isolate faulty downstream loads to propagate into your distribution system. And so now as the distribution system changes so much and the power that the nature of the voltage that we distribute is changing so much, we also need to adopt the protection scheme. And in general, one can say the most important thing that you need to improve is the speed, the fault isolation speed. And there we do need a substantial improvements by almost a factor of 10 to the power of 3. So it's 1,000 times faster fault isolation. And that can no more be achieved with electromechanical components. You need to introduce semiconductor solutions. These are then called the solid-state breakers.
This is the only solution to handling this kind of...
Seems so far. I mean, there's hybrid solutions, for sure, as always. When you have this huge transition, there's hybrid solutions as well that combine semiconductors with optimized electromechanical actuators. But when it comes to high-power distribution systems like we do see in the AI data centers, we predominantly see solid-state circuit breakers introduced.
Okay. Now, circuit breaker technology is nothing new. Obviously, it's been around for a decade. And you have said that solid-state circuit breakers revolutionize power distribution schemes. However, both technologies will coexist. So tell us what you meant by that.
Well, if you look into the electromechanical breakers, it is amazing. This technology has been actually patented about a century ago. A real century. So the original patent of this electromechanical circuit breaker was filed in 1925 in the German Reich. And since then, it has for sure seen a lot of evolution, but the basic technology is still the very same. So whatever you find in your household, whatever you find in most industrial installations, AC installations, is still based on that very scheme, which I think is impressive. With the solid-state breakers, we now enter a new era. I would actually call it a revolution, because they enable a much faster tripping, much more accurate tripping, and we enable a much lower overshoot. In the DC grid, we have a very, very fast rate of rise of a fault current that can rise like 400 to 500 amps per microsecond. And a solid electromechanical breaker takes like 10 milliseconds, 20 milliseconds to interrupt the fault. Now multiply 10 milliseconds by 500 amp per microsecond. That is a tremendous amount of current. With a solid-state breaker, we interrupt within microsecond regime. So you barely see any overshoot. So in the end, it's totally unspectacular. If you apply a solid-state breaker, there is no sparks. There is no smoke. There is no explosions anywhere. There's not even a click. So it's totally unspectacular. And that's exactly what a solid-state breaker should be.
Is this because it's happening so quickly?
It's happening so quickly, and there's no huge amount of power that you see there. You don't see hundreds of kiloamps getting interrupted because we interrupt exactly at where the fault current is. If the nominal current is like 100 amps, we would eventually see a maximum current of 500 amps, while with the electromechanical breaker, you would see 200 kiloamps. You can imagine if you want to interrupt 200 kiloamps, there will be sparks, there will be smoke, and you have to avoid that. This is not acceptable, especially in the data center environment. Okay. And this is then wear-free. That's also amazing that you can do hundreds, you can do thousands of fault interruptions, because this is wear-free switching. And the key benefit, therefore, is that you can use the circuit breaker also for additional functionality like actuation. It's possible, and it's also being used. So this is obviously substantially different from all legacy implementations. Now, the question is, will each and every socket now convert to a solid-state breaker because it's so cool and so more capable? Eventually in the future that might happen, but this will be the far future. It's clear that a solid-state breaker is definitely not cheaper than electromechanical one. And there's also a wide range of different requirements, especially in the AC domain. So what we do expect is that especially for high power, high voltage DC distribution, we will predominantly see solid-state breakers being applied. While in the AC domain, it might be some niche markets that start with the adoption. We already see that. And then over time, as the technology becomes more available, we will also see more sockets in the AC domain.
Okay. Now, my burning question is when we say solid state, we think of nothing mechanical, right? There's no moving parts. But this can't be the case in solid state circuit breaker because you do need this isolation between two points, right?
You seem to be an electrical engineer. Yes. In some implementations, it might be full solid state, especially in extra low voltage, as we used to use in the data centers, like for 48 volts. You don't have the need for galvanic separation, not necessarily from a safety perspective, right? But every trained electrician knows that you don't want to touch a live node, even though it says off. There will be some leakage currents, and especially with the capacitive nature of such a DC grid, that would be super dangerous. So every standard basically states that you have to have a galvanic separation, and semiconductors cannot provide that. You need to add an air gap device, like you have it with the electromechanical breakers as well. They would open, and then you have a galvanic separation. The big difference here is that now, if you look at the distribution of workload, we have a semiconductor switch, and we have this air gap device in series. That electromechanical actuator doesn't have to do the heavy lifting anymore, because the current will be actually decayed to zero by the semiconductor, and then you open the air gap device. That's also why we see a lot of players now in the market coming out with optimized disconnectors, because you don't need that fancy arc chamber anymore. You don't need all the kiloamp switching, the multiple kiloamp interruption capability. You just need to provide an air gap that can be done much more easier, much simpler, much more optimized than using this very large scale burning chambers to handle the arcs.
Which would make the device more durable down the road,
It makes it more durable. It also makes it less resistive. We shall not underestimate the resistance that comes with those disconnectors. These are also electromechanical contactors that have some resistance. You can optimize those contacts to have less resistance, and you can make them smaller, substantially smaller. And especially in the data center market, we see that power density is the key deciding criteria. You want to keep this contact. You add those breakers; they cannot be huge, and the smaller they are, the more appreciated it is. That's why it also makes sense to work on those disconnectors and optimize them for solid-state power distribution.
And you, as an engineer in this field, you're in a key position to talk about what might be the challenges. So I throw that out to you. What are the big hurdles that have to be overcome, or what do you see on a daily basis?
Well, yeah, one might say this is a super boring application, right? You're working on a thing that is sitting in a cabinet. You don't see it. It is on 24/7 for 15 years, and there might be no single switching action. So compared to my colleagues that work in the power conversion business, it's a sad application somehow, right? But in that 1 microsecond that this fault happens, it must do its job, right? And it's fully exposed. It does not have any input protection, does have no output protection. So obviously, the one time that it has to do its job in its lifetime, it's important. And if this thing fails, it can lead to substantial damage. It can lead to a blackout. In the best case, it can lead to a fire. And subsequent propagation of that failure might also lead to a harm to people. It's a protection device in the end. So it's obvious that you also want to keep the conduction losses of that semiconductor that we put in series now as low as possible, right? So on the one hand side, we need to optimize the technology that it is as low as possible, and it needs to be super reliable on the other hand side, and it needs to cope with that boring application environment just sitting there and not having to do anything. So that's a huge challenge for semiconductors as well. And that's also why like 4 or 5 years ago, we decided that we do need to develop dedicated semiconductor technologies, also packages that cope with these very particular requirements. And that's what we are currently working on. And that's also what we are already rolling out already on a first scale.
And earlier, you touched on this concept of moving higher voltage or bringing higher voltage into the rack. What does this mean for solid-state circuit breakers? Do you need more, fewer, faster? How do you compensate?
Yeah, it's not just the use of the increase of the voltage level. That's one thing, right? We are now rolling out a full distribution scheme, right? In the first implementations, we do see it's like a point-to-point connection. There, it's easy. You have one source, you have one load. You put eventually a breaker in between if the connection fails or whatever. Also for some protection of the source, for instance. But now what we do see is the next stage is that you really go into a grid. You have multiple sources that combine together to one distribution rail, and then you have multiple loads that tap from that distribution scheme. You need a hierarchy of breakers, and that is driving it. This is breathtaking as it's now being rolled out. We know that same distribution architecture from AC systems. And that's not also being rolled out for DC systems, although you can imagine that if you have this very fast rate of rise of the fault current and very fast tripping breakers, it's an enormous challenge to also make sure that those breakers are selective one versus each other. You don't want to have one small breaker having the job to trip, but it also would trip the upper one and the main one, and you also go into a blackout. So you need, despite being so fast, you need to achieve selectivity. So we need multiple sizes of breakers, ranging from like 30 amps on the individual rack level up to many kiloamps on the main breaker level. And that's the key requirement. They still need to be super fast. You cannot compromise on the reliability, and they need to work together. So the more complex these power distribution schemes are designed, the more breakers will be employed, and that's what is currently going on. They need to be faster. They need to be enormously capable, and they also need to be affordable. I think that's also an important part that you want to take the benefits for sure from solid-state technology, but it also needs to be commercially viable to be applied.
So bottom line, it sounds like things have just become really complex, and where we used to have a linear system, it's now become a grid.
It's becoming a grid in the end, and we as engineers, we like that complexity. We tackle it, and I think also with the products that we are now rolling out, it is demonstrated that it works. It's definitely cutting edge technology, although it doesn't look so sexy from the way it's working. When it's working, it is it is very interesting how it works together, and to make this thing reliable and robust and available as well. And that's what is being rolled out also together with our customers. We are working very closely there, and we'll see first systems in place by end of the year in a high power data center, and then looking forward how this gets then rolled out into the breadth of the market.
And this sort of leads me to my next question, which is commercial viability. It sounds like if we're moving forward with these systems, then we have to have these solid-state circuit breakers. Mm-hmm. Is the market welcoming this? Are they concerned about costs, or is this?
It would not be the market if they would not be concerned about the cost, right? And that is clear. And we know the cost of legacy AC systems, right? We know the benefits of the DC distribution. And it's clear that a breaker where you add a solid-state semiconductor, high-voltage solid-state device in series to a contactor will not be cheaper. I think that's the nature. What we do see is, as with every new technology, it's a matter of novelty, it's a matter of volume, also experience in the market, and also a matter of standardization. What do we have to cope with? What do we have to meet in terms of requirements? According to which standard will we certify such a breaker? Can we take out the overhead that is currently associated with a lot of standards that basically result from electromechanical breaker standards? They just have been derived a little bit, but still they're based on the electromechanical requirements. That is a huge cost burden as well. And I think the more those technology gets rolled out, the more it gets used, the higher the volumes. In semiconductor, it's all about volumes. Also, the more commercially viable will that be. That's why I mean that at the beginning, we'll predominantly see the solid-state breakers being employed in DC systems, where the value proposition is enormous. It's a must to apply them. And then we'll also see that we'll more and more see them being applied in AC systems, where eventually the value proposition you only have in some niche markets where you need particular requirements. But as the cost goes down, then it also becomes commercially viable. It gets very competitive, also versus electromechanical solutions.
So now, for our listeners who are interested in this topic, is there anything looking forward, looking into the future that we haven't talked about that might be key points when we discuss the solid-state circuit breaker?
Yeah, it's hard to say what happens in a revolution, right? If I would know that, it would be easy. Obviously, what we do see is, as I already mentioned, we see the voltages going even higher, going even beyond the limit of what is considered the low voltage regime, up to 1500 volts, especially in the context of solid-state transformers. We also see some first customer projects that are even dealing with voltages as high as 34.5 kilovolts. Now, imagine you do a solid-state circuit breaker that has at least a blocking capability of 60, 70 kilovolts. That is an enormous technological challenge. Also, isolation coordination-wise, we'll see a lot of things coming up there as well. I think on the standardization side, we have high hopes that we'll see dedicated standards that address the particular aspects of solid-state breakers, also the particular requirements in a DC grid. So far, there's not a big delta in the standardization between AC and DC, although those grids are substantially different. I think that's one thing. And also on the customer end, we do see, like in every revolution, there is a couple of customers that cope with that change, that address it, that even drive it. Some others are reluctant, and we'll see what the outcome is of that revolution. And that also gets new players into the market. They're just evolving. They eventually do not even have legacy products. So for them, it's a new a reason to enter that market. And that is also very interesting to see how that market is now evolving. It has been there the market is huge. It has been there for 100 years with the same thing, everybody optimizing to the last cent. And now we go with something that is high value, protecting enormous assets in a data center. So I think it's very interesting to see. And let's see in 2 years, we can talk about what happened. And this market is so super fast that I think in 2 years it will be a completely different picture.
Yeah, it's mind-boggling. I mean, it's something that's a technology that's been around for 100 years, but it's never ever moved so fast in the history of its life.
It got an impulse by DC distribution. Now, DC distribution was used in a lot of trial applications, also in other fields in the industry. Now, obviously, with the data centers embracing this technology, it gets an enormous technological push, and it also accelerates the rollout in other markets. I think that's why it is super amazing to see how things are developing, and it also got an enormous push for sure, also to take huge investments in product and technology development. It doesn't come for free, so it also needs to be justifiable to take this effort.
Thanks for taking time to talk with us today on the podcast, and we look forward to talking with you again in the future.
Welcome.
And thank you for all who are watching and listening. We hope you enjoyed the show, and we'll see you soon. Thank you.